Hi, Ben. I wanted to try to draw what I was explaining over the phone. So let's keep thinking of the age and earnings. So you might collect data, and there's definitely a positive relationship, but the data might look more like this, right? Now, a linear regression, which is the dependent variable as a function of an independent variable, there's usually a constant if it doesn't start in the origin, is assuming that this coefficient is the slope of the line. So the best fit line that this can do is, let's say, this, right? So it would mean that if you go the slope, an increase of 1 here, an increase of 1 here, so if this is 0, 1, and this is, 20 to 21, this slope, whether you're here or here, is exactly the same. It's a linear line. So let's say the beta 1 was estimated to be $1,000 or $200, whichever unit it would be at. But you can see that the data actually is not really straight, right? It's looking more like this. But given that it's a linear regression, it can't do that. So if we were to plug in, let's say, the age of 10, then the expected value of earnings at the age of 10 would be beta 1, which is 2, times x, which is our age. So 2 times 10, it would be 20. Now, if we change the model and add that quadratic term, so now we have x squared, what it does is when I'm expecting now, I want to try to figure out what the earnings is at 10, right? And let's say beta 2 is estimated to be negative 0.1, let's say. Now, my estimation of earnings at the age of 10 now would be still beta 1 times x, which is 2 times 10, but I would also add, and now this is a negative 0.1 times the x squared, so 10 squared. 10 squared is 100. Okay, maybe I should, hold on, add a 0. We'll do it 0. Let's see if I can, yay. Okay, 0. I made it too big. So 10 squared is 100, so this would be now 20 minus 10 squared is 100, 100 of that would be minus 1. So now this would be taking it down by 1 notch. So the person at the age of 10 would still get this coefficient of the straight increase, but by squaring it, it would take it just a tiny, tiny tad down. So this is the decrease of 1 from 20, let's say. Okay, so let's say we were at 20, and now it takes it down to 19 combined with the square term. Now, if you estimate this now for, let's say, a person, what would be the earnings at 20? If it was just a straight line, it would have been 2 times 20, so it would have been 40, right, in model 1. But if we add the square term, now we have the 40 minus 0.100 of 20 squared, which is 2 times 2 is 400. Hopefully I'm doing it right. And 1/100th of that is 4. So now this would be 36. So over here, for 10, we took it down just by 1. But for the person who is 20 now, they're still going to get this positive coefficient, but it's going to take it down by 4 because we're squaring the age and subtracting 1/100th of that. So when we do that, each additional year of age is going to give us a bigger diversion, I don't know if that's the right word, away from the straight line, and ultimately that's going to give us that curved relationship that we're looking for. So the total effect of age, we're combining the linear and the square term, and it allows us then to have the correct nonlinear form. But it's because it takes a negative, so it means it's a negative relationship. The bigger the age gets, the further away we get from the linearity. Now, if for some instance, some relationships in other forms might look like this, then that squared term, the beta 2, the coefficient then would be positive. It would mean that from this, it would be getting further and further away to the positive side from the linear relationship. So if the square term coefficient is negative, it means it's decreasing at the rate. If it's positive, it's increasing at the rate. Hopefully this helps.